regression. That is when you have multiple input variables, not just a single input variable like you do here. There's only one x1 variable or one x variable in this regression model. And we're going to review the case of simple linear regression, which is the model that's shown right here. And last time we talked about simple linear regression, we derived the equations for the estimate of the intercept and the equation to estimate the slope. Okay, and this should have a hat over it. So we'll do that now. And the hat just denotes that it's an estimate, so it's a minor thing. Um, the mean square error is given by this equation here. It's the actual observed value minus what's predicted by the model, all squared, divided by n minus k minus 1. And here we divide by n minus k minus 1 as a penalty for adding extra variables. So in the case of simple linear regression, k is just 1. And when you include two variables in your regression, that is two input variables, k would be 2. So k is just however many input variables you have in your regression model. And this thing, this mean square error, this actually estimates the variance, and it happens to unbiasedly estimate it. The data set that we were considering last time was the Galton data set, and we wrangled this data to only include sons. So we have the father's height, we have the child's height, and we restrict this data just to be a subset of the data of just sons or males. And we fit a linear regression to that. Okay. Um, the linear regression equation was given by this column with the coefficients right here. And that allowed us to form our simple linear regression equation. Okay, and that's where we left off last time we talked about this data set. What we're going to talk about now is the fact that these distributions, these estimates, so because we estimate the intercept, and the intercept is calculated from the data, and the data is random, it's randomly collected data, that means that the data has a probability distribution, okay? And the probability distribution of the estimator for beta 1 is a t-distribution with n minus 2 degrees of freedom. And the formula is given here for how to calculate this t-statistic. This t-statistic, right here, is provided by this column. So for the slope of father, we calculate that this statistic is 9.337, and we calculate this with beta 1 without the hat being set equal to 0. Okay. So here the null hypothesis, this value of beta 1 comes from the value of the null hypothesis. The null hypothesis associated with this is that beta 1 is 0, okay? And the alternative is that it's not. So maybe that'd be worth writing down. So here, the typical null hypothesis, although it could be any null hypothesis. It doesn't have to be zero, but what's provided in this output is that is zero, meaning it does not affect the output. Okay. The alternative is the two-sided alternative, um, that it's not zero, meaning it does affect the output. Okay. And here this should be beta 1. Okay. And let's just format this a little bit nicer. Okay. So that's our null and that's our alternative. So typically, uh, people write this as just being zero. So under, I should state under the null that this thing is zero. Okay. So let me move this here. So this is a distributional fact, which is this. Okay. And using this distributional fact, you can test hypotheses. And the distributional fact under the null hypothesis becomes this. So this. Okay. So that is the statistic under the null hypothesis. We just plug in 0 for beta 1. Okay. And then when we calculate that, we get this 9.33. Now, under the null hypothesis, we can calculate the probability that it's bigger than the given statistic, the t-distribution is. And we see that has a 0% probability. This is the p-value. Okay. So the p-value for this is 0. When the p-value is so far close to 0, um, it's less than 1%. So if we use 1% as the critical value, we're going to reject this null and conclude that the alternative is true. So the coefficient's not 0, and uh, that input variable affects the output. So one conclusion from this, because it could not be that this coefficient was 0, it couldn't be that case. What that means is that Galton's hypothesis of regression to the mean is not due to random chance. It is, in fact, a feature. Okay. The other thing that you can do is you can calculate a confidence interval using this t-distribution, just like we did before. And the confidence interval will suggest that the slope coefficient could be as small as 0.35 or as large as 0.54. So, anything between here would be a reasonable estimate for the coefficient. And this is your best estimate because that's what we calculated from the data. Okay. Notice that 0 is not in this interval, and that agrees with this p-value. So it's not likely that this coefficient could be 0. And uh, so that's how we can calculate uh, a confidence interval and test hypotheses using this distributional fact. Okay, and to test hypotheses, we do this. Okay. Okay. So doing this, we did this before. We saw that the cutoff value of 69.31, um, if we use a value that's bigger than this, like 75, and if we use a value that's smaller than this, um, the offspring is going to, on average, experience regression towards the mean. So the predicted values are formed from the equation, from the regression equation. So here, this 38.73 plus the coefficient uh, for the slope times the input variable 75 gives us the predicted value of 71.85. So they regress towards the mean because they're um, smaller than their father. They got closer to the average. Likewise, if your father is 65 inches tall, you're going to be taller than your father and you're going to regress or get closer towards the mean, okay, towards this equilibrium point of 69. Okay. Okay. So we checked the assumptions of a regression, which is that we have constant variance, so like the spread of these points is roughly the same no matter what the fitted value is, and that appears to be the case. There are a few outliers, but keep in mind things are random, so occasionally you can have things that are bigger or smaller than expected. Another assumption was that the errors, which is the residuals, are normally distributed. So if they lie on this theoretical quantile line that's in red here, then it matches if it lies on it, then the theory matches the observation, which it seems to do very well here. Two outliers that are to the right and two outliers that are to the left, so smaller or larger than average here. Then we could also display a histogram, and the histogram seems to work very well here. Okay. Okay, now independence, we commented last time that there seems to be some dependence in the data because entire families are used in the data set. And if I have a brother or a sister in the data set, my height would be correlated with my brother's height or my sister's height. So if I tend to be taller, my guess is that due to genetics, it would likely be that my brother would also be tall generally, right? So there's probably some dependence in the data, but it's not unreasonable. Okay. Now we're going to move on to multiple linear regression, but before we do that, we're going to consider the case of again a simple linear regression. Okay. Um, so suppose that I didn't wrangle the data. I used this entire data set of Galton data, and I regressed child height, where the child could be a son or a daughter, and I regressed that on father's height. Well, what I'd see is I'd see these coefficients change because the data changed. That's to be expected. Okay. Um, I can also get predicted values. And here, one thing that this is doing is this is just calculating in this cell, this is calculating the average height um, of fathers right here. Okay. And it's showing it to be 66.74. Okay. Um, so here's the predicted height uh, of an average father. This is the predicted of an offspring. So let me say that one more time. What this cell here does, this one here, is it's predicting the child's height based on the average height of the father. So if I input the average height of the father, tells me the predicted height of my offspring will be 66.74 inches. Okay. Now, this is interesting. The average height of fathers is 69 inches. The average height of sons, um, whose father's height are between 68 and 70 inches. And I included an interval there because there might not be enough fathers that are 69 inches exactly. So heights on a continuous range. So I used an interval, but it contains 69 inches, which is basically the average. It's a little under it. Um, then the average height of a son, um, for fathers in this range between 68 and 70 inches is 68 inches. Now, the average height of daughters whose fathers are the same height, 68 to 70 inches, is 63 inches. So notice it said, hey, you know, and notice I chose my interval 68 to 70, so 69 is like right in the middle, which is almost the average. So notice my predicted value for a father whose height is 69.19 inches predicted 66.74. So this seems problematic because the sons are on average are 68.98 inches. Okay. The predicted height of daughters is 63.86 inches. So 66 inches is the predicted height because I haven't accounted for gender. So I'm underestimating the height of sons. I'm overestimating the height of daughters, and it's kind of right in between, right? Well, what's going on here? Um, if I just looked at the residuals and I didn't look at it colored by males and females, I'd say everything's great. This resembles a normal distribution. It's not perfect, but it has some similarities to the normal distribution. But if I make a histogram of the errors and I color it by the gender of male or female, I can see, hey, the men have a normal distribution that's above average. The females have a distribution that's below average. And remember, if I have a residual of 0, a residual is the observed value minus the predicted value. So 0 means that I predicted it perfectly. What this is saying is that on average, or most of the time, I'm underestimating the height of sons or men, males, and I'm overestimating the height of daughters or females in my data set. So simple linear regression with just one input variable, right? Because here this is going to be child's height is equal to 40.13 plus 0.38 times father's height. That's going to be the regression equation. So just using one input variable leads me to consistently underestimate my sons, or underestimate sons and overestimate the height of daughters. Okay. So a better model would be to include father's height, but also the gender of the offspring. And now that I've included more than one variable, I'm in the case of what's called multiple linear regression. Not simple linear, but multiple linear. And let's look at this model. So to see if this model is indeed better. So notice I have an intercept, but I have two slope coefficients, one for gender male and one for father's height, just like before. Okay. Um, so here's the thing about this. Um, this gender male, if the gender of male is true, this variable gets a 1, Otherwise, it gets a 0 because notice I have I've included gender, and the genders listed in this data set are male and female. So to code that, it codes it as 0, 1. It coded the males as 1s, the females as 0. Okay, that's called a dummy variable. Okay. Okay. Um, let's see if I have the same problem with this model. So this is a plot of the residuals of this model, and it looks like it basically fixed it. On average, for both data sets, men and women, the average error is about 0. So it seems to have fixed this problem of underestimating the height of men and overestimating the height of the daughters or females. Okay, and indeed, I asked it, what's the average error? So for sons, it's minus 2.4, but notice this is times 10 to the minus 13th. That might as well be 0. Same thing for daughters. So basically no error on average. Okay. Let's talk about predicted values. So the predicted values based on a father's height on the x-axis is given by these two lines. Okay. The blue one representing males, the pink one representing females, and we see a constant difference in heights. These are called parallel lines, okay? And that's a feature of this model, okay? Um, so we'll talk about that again momentarily, but let's talk about uh, we'll come back to that, okay? Let's talk about the reason for this difference in this graph. And it comes down to writing out the regression equation. So that's why this is printed here. So to form the regression equation, I look at this column of the coefficients, and I take the intercept of 35.67. I take the slope of father's 0.41, multiply it by that variable that represents father's height. Then I take 5.18 times gender male. Okay. Now I was talking about the variable gender male, and here it is written down again. Okay. It's 1 if the condition is true, the individual's male. It's 0 if they're female or false. Okay. The coefficient of 0.41 indicates for each additional height, the child's height increases by 0.41 regardless of if they're male or female. Okay. Now, this regression equation, it's a really slick thing to do. Okay. I get two regression equations for the price of one. And statisticians really like this form of regression. Rather than wrangle the data and subset it into only sons or only daughters, I have two regression equations for the price of one. And I get to use all of my data in one regression equation. So because I use one regression equation, I have to estimate less things, but with more data. And that's the thing that statisticians like. If I if I have to subset my data into sons or daughters, I only get a subset of the data. I reduce the size of my data set. That's problematic, okay? And I have to estimate more things. The more things that I estimate, the more things that could be incorrectly estimated, okay? So this is the better statistical practice, is what was done here, to use this dummy variable, okay? And because I use this dummy variable, I can break it into two regression equations. I can put gender male, I can put a value of 0 for daughters' heights, and when I do that, I get exactly this. So the regression equation for daughter's height is exactly that. Then for sun's height, the other regression equation, I put a 1, and it changes this uh, intercept here, okay? And it changes it by 5.18, okay? If I was to subtract these two equations, so subtract daughter height from son's height, I would have a constant difference of 5.18, meaning that accounting for father's height, so if both fathers have the same height for the son and the daughter, then the difference in height between men and women is exactly 5.18 inches, and that is the difference here in these parallel lines. So it's just shifted up by 5.18, okay? Now, one thing that I note, and I'm just writing this out here, that we can calculate residuals based on the actual son or daughter's height, y sub I, minus what the equation predicts. So the observed minus predicted. Okay. Now we're going to come back to the regression output. We're just going to think about a few things in this regression output, namely these p-values. So notice the p-value right here for gender male is 0, up to 3 decimal places. The same for father. That tests the null hypothesis. So the null hypothesis is that that variable does not affect the output. The alternative is that it does affect the output. So for each regression coefficient, we know that it affects the output of son or daughter height, meaning I know that both of these variables should be included in the model because of this, the p-values of each. Okay, if the p-value was like 0.2, 0.12, 0.15, that would be an indicator you might want to remove that variable from the regression model. Okay, but we don't have that case. Now, if I look at these model assumptions, I can see from the QQ plot, things look pretty normal here. There are a few more points that are outliers, but it doesn't look too bad. Then here's the histogram with the residuals looking pretty normal as well. Okay. Looking at constant variance here, the spread of these points seem to be roughly constant. And again, we expect some dependence in the data.